Hey friend, welcome. If you're here to unwind, to calm your mind, or to fall asleep to something meaningful, you're in the right place. Tonight, we'll explore why the universe has rules at all. Gently, slowly, and with no rush. Just settle in and let the science carry you toward rest. Chapter 1. What does it mean for the universe to have laws? When physicists say that the universe has laws, they are not talking about laws in the legal or moral sense. They mean that the behavior of matter, radiation, space, and time follows regular patterns that can be described in a precise, usually mathematical way. If you drop a stone today in Belgrade and someone else drops a stone tomorrow on the moon, the same underlying rule describes how both stones accelerate and fall, even though the surroundings are completely different. The idea that there are such stable, general rules is so familiar now that it can be hard to remember how astonishing it really is. A law of physics, in the modern sense, is a compact statement about how physical quantities change or remain the same. It connects measurable things such as position, velocity, temperature, electric charge, or energy in a way that holds everywhere and every when, at least within some domain. The crucial words here are generality and invariance. Generality means the law does not just describe a single event, but applies to a vast range of situations. Invariance means that the form of the law stays the same, even when you translate the system in space, shift it in time, or view it from a different state of motion. The claim that the laws of physics are invariant under such transformations is another way of saying that nature is not playing favorites. The same rules hold here as there, now as then, for you as for me. This notion of invariance underlies some of the deepest ideas in physics. If the outcome of an experiment does not depend on where you perform it, the underlying laws are said to be translationally invariant in space. If they do not depend on when you perform it, they are invariant in time. If they do not depend on how you orient your laboratory, they are invariant under rotations. The modern view of physics treats these invariances not just as convenient features, but as guiding principles. The symmetries of the laws strongly constrain what those laws can look like. It is helpful to distinguish laws from models. A model is a description of a particular kind of system under particular conditions. For example, an ideal gas model describes a great many particles that do not interact except through elastic collisions. It is not literally true of any real gas, because real atoms and molecules always attract and repel each other to some degree. Yet the model, combined with more general laws of mechanics and thermodynamics, can make very good predictions about gases in many situations. The core laws in the background, such as conservation of energy or Newtonian dynamics at low speeds, are more fundamental than any single model. They are like the grammar of a language, while each model is like a specific story told using that grammar. The idea that there are universal physical laws is relatively recent in human history. Ancient cultures certainly noticed regularities: the rising and setting of the sun, the phases of the moon, the cycle of seasons, the motions of bright planets against the stars. They built calendars, tracked eclipses, and used these patterns for agriculture and ritual. But regularity by itself is not yet the concept of law. A law, in the modern sense, is expected to hold without exception and to apply to unfamiliar situations that have never been observed before. The conviction that nature is governed by such strict, exceptionless rules grew gradually during the scientific revolution in early modern Europe, through the work of thinkers such as Galileo, Kepler, and Newton, whose analyses of falling bodies and planetary motion showed that both everyday motion and celestial motion could be described by unified mathematical relations. From a philosophical perspective, there are different ways to understand what these laws actually are. One influential approach, often called a regularity view, treats laws as descriptions of the patterns that actually occur in nature, and nothing more. Another approach, sometimes called necessitarian, holds that laws express real connections of necessity in the world, which make the regularities hold. Physicists can work productively with laws without resolving this debate, but it is a reminder that beneath the technical use of equations, there are still open questions about what sort of thing a law of nature really is. Whatever one's preferred interpretation, certain features of physical laws are widely accepted. Laws are general rather than particular. They support counterfactual statements such as, if this mass were located here instead of there, the gravitational pull would change in a definite way. They are objective in the sense that they do not depend on who is looking or on what we believe. They are also, at least in our best current theories, expressed in mathematical form. This does not mean that every aspect of the universe is perfectly law-like. Many phenomena are governed by complex initial conditions, chaotic dynamics, or statistical behavior. But beneath this complexity, physics aims to uncover stable structures that cannot be violated, only instantiated in different ways. Another crucial distinction is between fundamental and effective laws. Fundamental laws, as the term is usually used, are meant to describe the behavior of the most basic degrees of freedom that exist in the universe, such as quantum fields in contemporary high-energy physics. Effective laws arise when you look at systems on larger scales or coarser levels of description and find regularities that do not refer to every microscopic detail. The laws of fluid dynamics, for instance, treat a gas or a liquid as a continuous medium with a density and a velocity at each point, even though at the microscopic level it consists of discrete atoms or molecules. These effective laws can be extremely accurate within their domain, yet they emerge from a deeper layer of description. The fact that there can be different levels of lawfulness stacked on top of each other raises subtle questions about which laws, if any, are truly fundamental. The concept of a law is also tightly connected to explanation. When we explain a phenomenon in physics, we often try to show how it follows from more general principles. The bending of light near the sun is explained by the curvature of space-time in general relativity. The spectrum of hydrogen is explained by quantum mechanics and the allowed energy levels of the electron. These explanations work because the specific behavior is seen as one consequence of a wider law. In this sense, laws occupy a privileged position in the hierarchy of explanation. They are not just one more fact among others, but the common source from which many facts can be derived. In modern physics, there is a further refinement. Many of the deepest laws are not about particular substances or forces, but about the structure of space-time and the symmetries of the underlying equations. The statement that the laws of physics are Lorentz invariant, for example, means that they take the same form in all inertial frames related by a certain group of transformations characteristic of special relativity. This is not a claim about any specific experiment, but about an overarching structural feature of a large class of non-gravitational interactions that have been tested so far. The shift from thinking of laws as lists of rules about specific things to seeing them as manifestations of deeper symmetries and structures is one of the characteristic moves of 20th century physics. In physics, invariance is also closely tied to conservation. Through the lens of Noether's theorem, every continuous symmetry of the action of a system corresponds to a conserved quantity. Time translation symmetry is associated with conservation of energy, space translation symmetry with conservation of momentum, and rotational symmetry with conservation of angular momentum. Even without going into the technical details, this connection illustrates how tightly stitched the fabric of lawfulness really is. All of these aspects together give some content to the claim that the universe has laws. It has stable regularities that can be expressed in mathematical form, that do not single out special places or times, that apply far beyond the situations in which they were first discovered, that are connected to symmetries and conservation principles, and that may exist at multiple levels of description. At the same time, there is still deep uncertainty about why these laws, rather than others, govern our world, and about what sort of existence such laws really have. Are they features of the universe independent of us? Or are they, in some subtle way, a projection of how our best theories organize experience? The empirical success of physics strongly suggests that there is something objective and robust behind the equations, but the precise metaphysical packaging remains a subject of debate and reflection. For the purposes of this journey, it is enough to hold on to a simple picture. The phrase laws of physics stands for the most stable, far-reaching, and deeply woven patterns that we have found in the behavior of the universe. Later chapters will explore how symmetries, fields, constants, and emergent phenomena give these patterns their particular shape. For now, you might picture the laws as an invisible framework that does not constrain you like a cage, but quietly supports the existence of stars, planets, and living beings. They make it possible for events to be connected rather than random, for causes to have reliable effects, and for minds like yours to learn, predict, and understand. As you are listening, you do not need to solve any equations or carry all of these distinctions in your head. It is enough to feel that behind the shifting details of everyday life, there is a deep, steady structure that does not depend on your mood, your mistakes, or your worries. The same laws that guide galaxies also guide the gentle motion of your breath. For tonight, you can let the thought of that quiet order hold you, and allow the questions that remain open to drift to the background, like distant stars fading into a calm, dark sky. Chapter 2. The Language of Nature. Why Physics is Written in Mathematics. When physicists say that nature is written in the language of mathematics, they are not making a poetic comparison. They are pointing to something that becomes increasingly difficult to ignore the deeper one looks into the structure of the physical world. Mathematics is not simply a convenient tool we invented to make sense of things. It is woven into the behavior of the universe itself in a way that consistently surprises even the people who use it every day. The motion of planets, the vibration of atoms, the bending of space-time, the flow of heat, the interference of waves, the distribution of galaxies, and even the behavior of elementary particles all follow patterns that can be expressed with mathematical precision far beyond what ordinary experience would suggest. To understand why this is so, it helps to begin with something simple. Imagine you toss a ball into the air. You could describe what you see in ordinary words. The ball rises, slows down, pauses for a moment, then falls again. But this description, while true, is vague. It leaves out details about the speed, the height, or the timing. If you repeat the throw 100 times, the pattern will be similar each time. But it will be difficult to capture that similarity in ordinary language. Now imagine you describe the motion using a mathematical relation that expresses how the height changes with time and how the velocity changes under the pull of gravity. Suddenly, the pattern becomes exact. You can predict where the ball will be at any moment and how fast it will be moving. You can explore situations you have never seen, such as tossing the ball on a different planet with a different strength of gravity. What began as a vague observation becomes a precise rule. And that rule holds not only for balls, but for any object under similar conditions. Mathematics does not just describe, it unifies. This unifying power is one of the reasons mathematics is so central in physics. Patterns that look unrelated on the surface often turn out to share the same mathematical form. The motion of a mass on a spring, the oscillation of an electrical circuit, and the vibration of an atom inside a molecule can all be described with the same kind of equation. The spreading of heat in a solid, the diffusion of perfume in a room, and certain kinds of quantum mechanical wave behavior follow the same general mathematical pattern. Even the shape of a soap film stretched across a wire frame and the curvature of space-time around a star have surprising structural similarities when written in mathematical terms. What this shows is that mathematics is not simply a way of recording observations. It reveals deep relationships that are not obvious from the raw experience alone. Mathematics also provides a way to state laws in their simplest possible form. A verbal description of a complex phenomenon can be long and ambiguous, but a mathematical statement compresses the essential content into something clear and testable. This compression allows physics to build theories that apply across enormous ranges of scale, from the behavior of the tiniest particles to the structure of the largest clusters of galaxies. It is remarkable that the same few concepts, expressed mathematically, can capture patterns across such extreme differences in size, temperature, density, and energy. The capacity for this kind of universal description is one of the defining features of a physical law. Another reason mathematics is so effective is that it naturally expresses relationships. Physics is concerned with how one quantity depends on another, how velocity depends on force, how pressure depends on temperature, how energy changes with configuration, how the curvature of space-time depends on the distribution of matter. Mathematics provides a precise way to express these dependencies. It can capture not just approximate tendencies, but exact functional relationships. With these relationships in hand, physicists can make quantitative predictions that can be tested against observation. If the predictions match, confidence in the underlying structure grows. If they fail, the structure must be revised, sometimes in ways that lead to deeper insights. It is important to note that mathematics itself does not tell us which quantities to relate. The physical concepts come from observation, experiment, and creative reasoning. Physicists must choose which variables matter, which approximations are reasonable, and which assumptions can be justified. But once those choices are made, mathematics provides the framework that binds everything together. It tells us what follows logically from the assumptions, and it prevents us from slipping into reasoning that feels plausible but is actually inconsistent. The power of mathematics in physics is also tied to its ability to generalize. When a law is expressed mathematically, one can often extend it to regimes that were not originally considered. This is not always correct, but when it is, the results can be profound. Early formulations of classical mechanics were extended to include more complex systems, eventually leading to the development of statistical mechanics and thermodynamics. Classical descriptions of waves helped open the door to quantum mechanics, where wave functions express probabilities rather than physical vibrations. The mathematics of curvature, originally developed in a purely abstract context, turned out to be the key to describing gravity as a feature of space-time itself. In these cases, mathematics enabled a leap beyond the original domain of application, revealing new layers of structure. Mathematics also plays a role in reducing ambiguity. Everyday language is full of words that can be interpreted in multiple ways. Physics needs concepts that are defined precisely. A term like energy, which appears straightforward in ordinary conversation, has a very specific meaning in physics. Mathematics gives that meaning a concrete form. It specifies exactly how to calculate energy in different situations, and how that calculated value relates to other aspects of the system. Without this precision, many physical concepts would be too vague to support accurate predictions. The question of why mathematics is so successful in describing nature has puzzled scientists and philosophers alike. It is not obvious in advance that a tool created by humans, originally for counting, geometry, and logic, should align so well with the structure of the natural world. The success is so striking that some thinkers have wondered whether mathematics is discovered rather than invented, as if it reflects an underlying order that exists independently of our minds. Others argue that mathematics is effective because we have shaped it over centuries to capture those kinds of patterns that appear consistently in nature. Both views have merits, and neither undermines the practical insight that mathematical reasoning is indispensable for deep physical understanding. One of the most intriguing aspects of mathematics is that it sometimes predicts phenomena that have not yet been observed. When theoretical reasoning leads to a new relation or a new kind of behavior, physicists may search for evidence to confirm the prediction. If the evidence appears, it strengthens the idea that the mathematical structure was capturing something real, not simply a human fantasy. There are many celebrated examples of this in the history of physics. What matters in these cases is that the mathematics revealed a possibility that had not been explicitly considered, and the universe turned out to allow that possibility. The correspondence between mathematics and physical reality is not limited to simple systems. Even in complex, chaotic, or statistical regimes, mathematical structures often appear. Weather patterns, turbulent flows, biological networks, and quantum many-body systems can all exhibit regularities that can be captured mathematically, albeit through more sophisticated or approximate frameworks. These mathematical descriptions may require more nuance, and their predictions may be statistical rather than exact, but the underlying principle remains. The behavior of nature is, at its core, patterned enough to be expressed through structured reasoning. One should not conclude that everything in the universe is perfectly mathematical. There are limits to what we can predict, and there are systems whose behavior depends sensitively on initial conditions or on details that cannot be measured precisely. But even in these systems, mathematics helps clarify what can and cannot be known. It provides bounds, approximations, and probabilistic descriptions that still reflect the underlying structure. Physics does not claim that all events are predictable in detail. Rather, it claims that there are governing patterns and constraints, and mathematics is the medium through which those constraints can be articulated. Mathematics is also essential for connecting theories at different scales. The physical world displays layers of organization: atomic, molecular, biological, planetary, and cosmic. Mathematics helps build bridges between these layers, reducing one set of principles to another when appropriate, or showing where new rules emerge. This ability to cross scales is one of the reasons physics can be both unified and diverse. The same mathematical reasoning allows us to study everything from the behavior of electrons in a solid to the evolution of stars and galaxies. There's a deep philosophical question at the heart of all this. Do we describe the universe mathematically because it is inherently mathematical, or because mathematics is the most flexible and accurate language we have developed? The question is not easy to answer. The success of mathematics and physics suggests that the universe has a structure that is at least compatible with mathematical description. But whether the universe is, in some ultimate sense, mathematical in its essence, remains an open question. What is clear is that any attempt to understand the laws of nature without mathematics quickly runs into limitations. As you reflect on this, it may help to recognize that mathematics does not belong only to experts or specialists. It is one way the universe speaks to us, through patterns of motion, rhythms of change, symmetries, and relations that connect distant phenomena. Whether you are aware of it or not, your everyday experience is shaped by these patterns. When you listen to music, when you notice the cycles of day and night, when you sense the regular beating of your heart or the steady flow of your breath, you are already participating in the deep order that mathematics helps reveal. And at the end of this exploration, when thoughts begin to soften and the day starts to fade, there is something comforting in knowing that the universe is not arbitrary or chaotic. Beneath all movement and change, there is a quiet structure that does not depend on our worries, our rush, or our uncertainties. You can let that structure hold you for a while. You can rest in the thought that even as everything shifts around you, the gentle order of the cosmos continues, steady and unhurried, carrying you through the night. Chapter 3. Symmetry, the quiet architect behind every law. When physicists speak of symmetry, they are not referring to superficial patterns or aesthetic balance. They mean something deeper and more structural, something that lies beneath the appearance of physical systems and governs the way the universe behaves. In physics, a symmetry is a transformation you can apply to a system that does not change the essential content of the laws describing that system. If you shift a laboratory a few meters to the left and perform the same experiment, the results do not change. If you rotate a particle accelerator or tilt a telescope, the underlying physical rules do not become different. If you run an experiment tomorrow instead of today, the laws you rely on remain intact. Symmetry, in this sense, is the quiet guarantee that the universe will not behave differently based on arbitrary choices of viewpoint, position, or timing. It ensures that the laws of physics do not play favorites. Symmetry has always been a part of physics, even before scientists had a formal term for it. When ancient observers noted that the rising and setting of the sun followed a predictable rhythm, or that the stars returned to similar positions each year, they were observing regularities linked to symmetry in time and rotational invariance of the sky. But the explicit recognition of symmetry as a fundamental principle of nature is a relatively modern insight. Over the past few centuries, it has become clear that symmetry is not merely a feature of the universe. It is one of the primary reasons that physical laws have the forms they do. A simple example can illustrate the essence of physical symmetry. Imagine standing in an empty field and dropping a stone. Now imagine moving a few steps to the right and dropping another stone. The surroundings have changed, but the gravitational acceleration is the same. The physics does not depend on your location. This feature is known as spatial translational symmetry. Nature does not care where in space the event occurs. The laws governing the fall of the stone remain identical. Similarly, spatial rotational symmetry means the laws do not depend on the direction you face. Whether you drop the stone while looking north or south, the rules of gravity remain unchanged. These examples might seem almost trivial, but they reveal something profound. Symmetry tells us that the laws of physics are built in a way that does not change under certain transformations. It is this invariance that gives laws their universality. Without it, each region of space or each moment in time might demand its own set of rules, making the behavior of the universe vastly more complicated and unpredictable. As physics developed, the concept of symmetry expanded beyond simple geometric transformations to encompass more abstract forms. One of the most important advances came from the study of electromagnetic phenomena. In the 19th century, James Clerk Maxwell unified electricity and magnetism into a single theoretical framework. Within this framework, the laws exhibited a subtle kind of symmetry. If you shift the electric potential and magnetic potential in particular coordinated ways, the observable electric and magnetic fields remain the same. This kind of symmetry, which does not involve moving through space or rotating a system, is called a gauge symmetry. It reflects the idea that some features of a mathematical description are not physically meaningful on their own, but only in combination. Gauge symmetry would eventually become one of the cornerstones of modern particle physics. It is the organizing principle behind the standard model of particle interactions, dictating how particles, such as electrons and quarks, interact with fields that carry forces. Rather than viewing forces as mysterious influences acting at a distance, gauge symmetry provides a structural explanation for why those forces exist and how they behave. In this sense, symmetry does not simply constrain laws, it generates them. The types of interactions that can exist in nature are directly tied to the symmetries of the underlying fields. Another important form of symmetry is reflection symmetry, sometimes called parity. This symmetry asks whether the laws of physics remain the same if left and right are swapped. For centuries, physicists assumed that nature made no distinction between left and right. But in the mid-20th century, experiments showed that certain interactions, specifically those involving the weak nuclear force, violate parity symmetry. This discovery was shocking at the time because it revealed that symmetry is not absolute. Some symmetries are exact, some are approximate, and some are broken in particular circumstances. The breaking of symmetry can itself be a rich physical phenomenon, capable of generating complex structures or triggering transitions in the behavior of matter. Symmetry breaking is central to many areas of physics. When water freezes into ice, the fluid state has full rotational symmetry, meaning the molecules are equally likely to move in any direction. In the solid state, the molecules settle into a crystalline lattice with specific directions preferred, and the symmetry of the system is reduced. This broken symmetry gives rise to new properties. The crystal has rigidity, it supports vibrations in discrete modes, and it can exhibit patterns that were absent in the liquid phase. Similar processes occur in particle physics, where the breaking of certain symmetries gives particles their masses and shapes the behavior of fundamental forces. One of the most elegant aspects of symmetry in physics is its relationship with conservation laws. This connection was uncovered through the work of mathematician Noether in the early 20th century. Noether showed that for every continuous symmetry of a physical system, there is a corresponding conserved quantity. Time symmetry, the fact that the laws do not change with time, implies conservation of energy. Spatial translational symmetry implies conservation of momentum. Rotational symmetry implies conservation of angular momentum. These relationships are not coincidences. They are mathematical necessities. Symmetry does not merely accompany conservation, it explains it. It is difficult to overstate the significance of this insight. Conservation laws are some of the most powerful tools in physics. They allow predictions even when the full details of a system are unknown. They provide checks on experiments, guide the construction of new theories, and form the backbone of much of classical and quantum mechanics. By linking these laws to symmetry, Noether revealed a unifying principle that ties together domains of physics that might otherwise seem unrelated. Her work shows that the universe's most fundamental invariances are responsible for the stability and coherence of the physical world. Symmetry also plays a role in determining which physical theories are possible. When constructing new models of particle behavior or cosmological evolution, physicists often begin by identifying the symmetries that must be preserved. These symmetries restrict the form of the equations and interactions, narrowing the possibilities dramatically. In some cases, symmetries can even determine the entire structure of a theory. This is especially true in quantum field theory, where symmetry groups dictate how particles transform and how forces arise. Without symmetry as a guiding principle, the mathematical landscape of possible theories would be enormous and unmanageable. In the realm of cosmology, symmetry appears in the assumption that the universe is homogeneous and isotropic on large scales. This means that, averaged over vast distances, the universe looks the same in all directions and at all locations. This symmetry underlies the models used to describe the expansion of the universe, the distribution of galaxies, and the evolution of cosmic structures. Even small deviations from symmetry, such as the tiny temperature differences in the cosmic microwave background radiation, carry deep significance. These deviations trace the seeds of structure formation and reveal how symmetry was broken in the early universe, allowing galaxies, stars, and planets to emerge. Not all symmetries are visible. Many act in the abstract space of internal properties, such as charge, flavor, or spin. These internal symmetries help categorize particles, determine how they transform and constrain their interactions. In modern physics, particles are often understood less as indivisible building blocks and more as excitations of fields that obey specific symmetry rules. This shift in perspective reflects a deeper truth. Symmetry is not simply an attribute of the universe. It is one of the fundamental scaffolds on which the universe is built. Despite its central role, symmetry is not an absolute principle. Some symmetries are approximate, others are broken in subtle ways. There are ongoing questions about whether certain symmetries that appear to hold in current experiments might fail at higher energies or in more extreme environments. The interplay between symmetry and its breaking shapes much of the current research in particle physics and cosmology. Scientists continue to investigate whether deeper symmetries exist beneath the ones we know, just as earlier generations discovered hidden structures beneath the symmetries familiar in classical mechanics. At a conceptual level, symmetry offers a way of understanding why the universe is comprehensible at all. If the laws of physics depended on your location, orientation, or the precise moment at which you performed an experiment, predicting anything would be vastly more difficult. The regularity we rely on both in science and in daily life is possible because of these invariances. Symmetry tells us that the universe is stable enough for patterns to exist, and those patterns are what allow us to learn, understand, and navigate our world. And as the day winds down, it can be soothing to realize that beneath the shifting details of experience lies a quiet order that does not depend on effort or expectation. Symmetry means that wherever you are, whatever the hour, the deep architecture of the universe remains steady. You can let that steadiness hold you for a moment. You can let the idea of an underlying order soften the noise of the day, reminding you that even in moments of uncertainty, the universe keeps its quiet balance, extending a kind of calm that you can carry with you into rest. Chapter 4. Noether's Theorem: How Symmetry Creates Conservation. There are moments in the history of physics when a single insight does not merely solve a problem, but reshapes the entire landscape of scientific thought. Noether's theorem is one of those rare insights. It stands among the most profound contributions ever made to our understanding of the natural world, not only because of its technical depth, but because of the conceptual clarity it brings to the relationship between symmetry and physical law. The idea in its essence is simple enough to state in words. For every continuous symmetry of the laws of physics, there is a corresponding conserved quantity. But like many simple statements in physics, it carries enormous weight. To appreciate what this means, it helps to step back and consider what a conserved quantity is. In physics, conservation does not refer to saving or protecting something, but to the idea that certain properties of a system remain constant as the system evolves. Energy, for example, does not spontaneously appear or vanish. Momentum, in the absence of external influences, remains unchanged. Angular momentum persists unless acted on by a torque. These statements are not guesses. They are among the most reliable principles in all of science. They allow physicists to trace the evolution of planets, particles, fluids, and fields with extraordinary confidence. Before Noether's work, these conservation laws were known, and they were central pillars of both classical and early modern physics. but their origin was somewhat mysterious. Why, for instance, should energy be conserved at all? Why should it be possible to define momentum or angular momentum in a way that remains fixed across all physical processes? The laws of physics stated that these quantities were conserved, but they did not explain why nature should behave that way. What Noether discovered was a deep and necessary connection between the symmetries of physical laws and the existence of these conserved quantities. Symmetry, in the sense physicists use the term, refers to transformations that do not change the form of the laws themselves. If shifting a system in space does not alter the laws, that is spatial translational symmetry. If rotating a system leaves the laws unchanged, that is rotational symmetry. If shifting the system forward or backward in time leaves the laws intact, that is time translational symmetry. Noether showed that these invariances are not merely aesthetic or convenient. Each one mathematically requires a corresponding conservation law. The connection becomes clearer when we consider specific examples. Time translational symmetry, the idea that the laws remain the same from one moment to the next, implies that energy is conserved. This means that the very existence of a uniform flow of time is tied to the stability of energy in physical processes. Spatial translational symmetry implies the conservation of momentum. Because the laws do not depend on where in space you perform an experiment, the total momentum of an isolated system remains constant. Rotational symmetry implies the conservation of angular momentum. Because the laws do not depend on orientation, the twisting or spinning quantity of a system cannot change by itself. These relationships are not accidents. They arise from the structure of the laws themselves. Noether's theorem formalizes the idea that symmetries give rise to conservation laws, and conversely, that conservation laws signal the presence of underlying symmetries. The theorem applies not only to classical systems, but also to the modern theories that govern particles, fields, and spacetime. In quantum mechanics, for example, conservation laws continue to reflect underlying symmetries, although the framework differs from classical mechanics. In quantum field theory, Noether's theorem is used to identify currents and charges associated with internal symmetries, such as those governing the behavior of elementary particles. This relationship between symmetries and conservation is one of the clearest examples of how mathematics reveals the underlying architecture of nature. Symmetries are expressed through transformations that leave the action of a system unchanged. The action is a particular quantity constructed from the variables that describe a system and their changes over time. Noether's theorem shows that whenever the action remains unchanged under a continuous transformation, there must be a corresponding quantity that does not change as the system evolves. This link between invariance and constancy turns the idea of symmetry from a descriptive tool into a generative principle. What makes Noether's theorem especially powerful is its wide applicability. It is not restricted to simple mechanical systems or to special cases. It applies to systems with fields, to systems with multiple interacting components, to classical and quantum theories, and even to theories of space-time geometry. In the context of general relativity, for example, symmetries of space-time itself correspond to conserved quantities such as energy, momentum. The interplay between geometry and conservation is more subtle in curved spacetime, but the spirit of Noether's insight remains central. Beyond its technical implications, Noether's theorem reshapes our understanding of what a physical law is. It suggests that the most stable features of the universe are not arbitrary, but arise from the symmetries of the underlying structure. This perspective turns the concept of a law from something imposed on nature into something emerging from deeper properties. Rather than asking why energy is conserved, we ask what symmetry gives rise to that conservation. Instead of treating momentum as a primitive quantity, we see it as the consequence of spatial uniformity. The laws of nature become the manifestations of symmetry. Symmetry breaking also becomes more meaningful in light of Noether's theorem. When a symmetry is intact, a corresponding conservation law holds. When a symmetry is broken, the conservation law may be altered or lost. This can lead to rich and complex dynamics. In particle physics, for example, the breaking of certain symmetries gives particles their masses and defines the structure of interactions. In condensed matter systems, broken symmetries underlie the behavior of crystals, superconductors, and superfluids. Even phenomena such as phase transitions can be understood in terms of changing symmetry patterns. Noether's theorem provides the conceptual framework for understanding these transitions, even when its direct mathematical form does not apply. Another important aspect of Noether's work is that it helps unify diverse areas of physics. Conservation laws appear in many contexts, from planetary motion to electromagnetism to quantum interactions. By showing that these laws arise from a common principle, Noether's theorem helps reveal the deep coherence of physical theory. The same reasoning that explains why energy is conserved also explains why charge is conserved in electromagnetic interactions. The invariance of the electromagnetic field under certain transformations leads to the conservation of electric charge. This is not a coincidence, but a manifestation of a common principle linking symmetry to constancy. As physics advances, Noether's theorem continues to serve as a guiding principle. In the search for new theories that might unify the fundamental forces, physicists often explore symmetry groups that extend or generalize the ones in current use. These symmetries dictate which types of particles and interactions can exist. They also suggest how different forces may be related. Even when experimental evidence is lacking, symmetry serves as a compass pointing toward promising theoretical directions. This is not merely speculation. Many of the greatest advances in physics, including the formulation of the Standard Model, have been shaped by symmetry-driven reasoning supported by Noether's framework. The elegance of Noether's theorem also raises deep philosophical questions. Why should the universe exhibit such symmetries at all? Why should time and space be uniform in the ways that give rise to conservation laws? These questions touch on the foundations of physics, cosmology, and metaphysics. Some of the symmetries we observe may be the result of the universe's initial conditions. Others may be necessary for any universe with stable structures. Still others may reflect deeper mathematical principles yet to be discovered. What Noether's theorem provides is not the final answer to these questions, but a beautifully clear connection between them. In reflecting on this chapter, it can be calming to recognize that the stability you experience in the world, your ability to rely on consistent patterns, on steady rhythms, and on the reliability of cause and effect, is mirrored in the structure of the universe itself. Conservation laws, born from symmetry, ensure that the universe has a kind of internal steadiness. Even as everything moves, grows, changes, and evolves, certain quantities remain constant, anchoring the flow of physical processes. This anchor is not imposed from outside. It arises naturally, quietly, from the deep symmetry of the cosmos. As you prepare to rest, you might let that symmetry settle into your thoughts. Beneath every motion lies a pattern that does not waver. Beneath every moment lies a continuity that does not fade. And just as the universe holds its conserved quantities gently but firmly, you can allow the steady structure of the night to hold you, letting the noise of the day drift away into stillness. Chapter 5. Fields and Forces, Where Physical Laws Live. When we imagine the universe, it is tempting to picture it as a collection of objects drifting through empty space. Stars burning in the void, planets orbiting them, molecules vibrating, particles colliding. For much of human history, this object-based view seemed sufficient. Yet as physics matured, it became clear that objects alone were not enough to explain how the universe works. Something deeper had to exist beneath them, a kind of invisible structure that extends everywhere, shaping how matter moves and how forces arise. That structure is the realm of fields. A field, in the language of physics, is something that has a value at every point in space and time. Temperature in a room can be thought of as a field. The air is warmer in some regions and cooler in others, and every location has a definite temperature at every moment. But physical fields go far beyond temperature or pressure. Electric fields, magnetic fields, gravitational fields, and the quantum fields underlying elementary particles define the true architecture of reality. Instead of thinking of forces as mysterious pulls or pushes acting across empty space, physics now understands forces as the ways fields influence the behavior of matter. This idea began to take shape in the 19th century, when the nature of electricity and magnetism was still being uncovered. Through a series of experiments, it became apparent that electric charges could influence one another even when they were not touching, and that magnets could do the same. The early language of action at a distance, inherited from Newtonian gravity, attempted to describe these effects without any medium between the objects. But this kind of influence, instantaneous and unmediated, remained conceptually troubling. James Clerk Maxwell's equations offered a clearer picture. They described electric and magnetic effects as aspects of an electromagnetic field filling all of space. Charges and currents did not act directly on each other. They shaped the field, and the field in turn shaped the motion of charged matter. The field was not an abstract idea or a convenient fiction. It was a physical entity. The same shift occurred in our understanding of gravity. In Newton's theory, mass exerts a force on other mass across empty space. In Einstein's theory of general relativity, mass and energy curve spacetime itself, and free objects follow the natural paths in that curved geometry. The gravitational field is no longer a force but a geometric distortion of the fabric through which objects move. Space becomes dynamic, geometry becomes physical, and gravity becomes a manifestation of the structure of the field, rather than a pull transmitted across the void. Fields do more than explain how forces operate. They provide the medium in which physical laws reside. In classical mechanics, one can describe motion using forces directly, but in modern physics, forces are understood as the ways fields interact. The electric force emerges from the structure of the electromagnetic field. The strong and weak nuclear forces, which govern the behavior of subatomic particles, arise from quantum fields with their own symmetries and interactions. Even mass, Something once thought to be a property of objects is now understood through the interaction of particles with a field permeating the universe. Quantum field theory takes the idea of fields to its logical conclusion. In this framework, particles are not tiny solid spheres but excitations, ripples of underlying quantum fields. Each type of particle corresponds to a different field. Electrons come from the electron field, photons from the electromagnetic field, quarks from their respective fields. The fields themselves are fundamental. The particles are their manifestations. This view resolves many conceptual issues that arise when trying to treat particles as basic. For instance, the creation or annihilation of a particle is simply the field changing from one pattern of excitation to another. One remarkable feature of fields is that they provide continuity where objects offer discreteness. Objects can appear or disappear, but the fields are always present. Even in an apparently empty region of space, the fields persist. They may have no excitations in that region, but the possibility for excitation remains. This is why modern physics treats empty space not as nothing but as a kind of physical medium, structured by fields, capable of supporting waves, fluctuations, and interactions. Forces arise naturally in this picture. What we call a force is simply the way a particle responds to the structure of the field through which it moves. A charged particle accelerates because the electromagnetic field has a particular shape in its vicinity. A mass curves space-time, and other masses follow the curves. The strong nuclear force arises because quarks interact with the gluon field in a way governed by specific symmetries, leading to confinement and the beautiful complexity of atomic nuclei. The weak force, responsible for processes such as radioactive decay, is tied to yet another field, one whose properties are subtly intertwined with symmetry breaking in the early universe. One of the greatest strengths of the field concept is its locality. In classical physics, forces that seemed instantaneous posed conceptual difficulties. Fields resolved this by providing a continuous mechanism through which information and influence propagate. A disturbance in a field travels at a finite speed, typically the speed of light. When a charge moves, it does not instantaneously affect distant regions of space. Instead, changes in the electromagnetic field propagate outward like ripples on a pond. This locality aligns well with relativity, which asserts that nothing, not even information, can travel faster than light. The field concept therefore serves as a bridge between our understanding of forces and the geometric structure of space-time. Fields also allow for a rich interplay with symmetry. In earlier chapters, we saw how symmetries can generate conservation laws. In the context of fields, symmetries go further. They dictate which kinds of fields can exist and how they interact. Gauge symmetries in particular specify the structure of electromagnetic, weak, and strong interactions. They shape the equations governing these fields and determine the form of the conserved quantities associated with them. The standard model of particle physics is built almost entirely from symmetry principles applied to fields. Without these symmetries, the list of possible interactions would be far larger and far less structured. Another important aspect of fields is their capacity for energy storage. The electromagnetic field can contain energy even in regions where no charged particles are present. This stored energy can later be released, influencing particles or radiating outward as light. In general relativity, energy stored in the gravitational field itself influences the curvature of space-time. In quantum field theory, The energies of fields give rise to phenomena such as particle creation, vacuum polarization, and the subtle fluctuations that shape the behavior of the vacuum. The idea that fields are fundamental has deep philosophical implications. It suggests that the universe is not primarily a collection of solid matter, but a network of interacting fields, each extending across all of space. The material aspect of the world, particles, atoms, molecules, emerges from these fields, but the fields themselves form the underlying fabric. This perspective blurs the boundary between objects in space, between substance and geometry. In a very real sense, the universe is more like a symphony of fields than a warehouse of objects. Despite their abstract nature, fields are tested and confirmed through experiment. The bending of starlight near the sun, the fine structure of atomic spectra, the behavior of high-energy particles and accelerators, the stability of matter itself, all these phenomena align with the field-based description. Every major advance in physics over the past century has strengthened the role of fields as the true carriers of physical law. There are still mysteries. Some fields predicted by theory remain difficult to detect. The nature of dark matter and dark energy, which appear to dominate the large-scale behavior of the universe, may involve fields we do not yet fully understand. The unification of fields, especially gravity with the quantum fields of particle physics, remains one of the great open problems of science. But the overall framework is robust. Forces arise because fields respond to the presence of energy, momentum, and charge. Conservation laws arise because symmetries constrain the structure of fields, and the richness of the physical world arises because fields can interact, fluctuate, break symmetries, and form complex patterns. As you reflect on this picture of reality, it becomes clear that the universe is not built from isolated pieces, but from a continuous fabric that allows everything to influence everything else. The fields that fill space also fill the space within you. The electromagnetic field governs the chemistry of your cells, the gravitational field shapes your weight on the earth, and the quantum fields underlie the particles that make up your body. In a very real sense, you are part of the same network of fields that forms stars and galaxies. And at the end of the day, when you sit quietly in your room or lie down to rest, it is soothing to remember that these fields do not depend on your thoughts, your worries, or the noise of the moment. They remain steady, woven through the universe in ways that allow stability, structure, and meaning to arise. You are held within that fabric, gently and without effort, just as every atom and every star is held. Let that quiet continuity ease the mind and soften the edges of the day, settling you into the calm flow of the night. Chapter 6. Constants of Nature, the Universe's Unchanging Numbers. One of the most striking features of the physical world is that, beneath all its diversity and complexity, there exist certain quantities that never seem to change. They do not drift over time, they do not vary from place to place, and they do not depend on who is measuring them. These special quantities, known as the constants of nature, act as fixed anchors in the fabric of reality. They appear in the fundamental laws of physics in the same way that the shape of a key determines whether it will open a particular lock. If the constants were even slightly different, the universe as we know it would be unrecognizable. Stars might never form, atoms might be unstable, or chemistry might be impossible. The cosmos is built around these unchanging numbers. A constant of nature is not just any number we encounter in physics. Some quantities appear to be constant only because of the particular situation we are studying. A piece of metal may expand at a certain rate with temperature, but that rate depends on the material. A planet may orbit its star with a fixed period, but that period is specific to one system. True physical constants stand apart. The speed of light in a vacuum, the gravitational constant governing the strength of gravity, the reduced Planck constant associated with quantum behavior, the charge of the electron, the masses of fundamental particles, and the fine structure constant that controls electromagnetic interactions. These numbers appear everywhere in physics. They are woven into the equations that describe nature at the deepest level. The speed of light in a vacuum, for example, is not simply the speed of light. It is a fundamental limit woven into the structure of space-time itself. It determines how fast information can travel and shapes the causal structure of the universe. Whether we are dealing with radio waves, gamma rays, or the glow of a candle, the speed remains the same. It is not a property of light alone, but of space-time. The constancy of this speed serves as a cornerstone of relativity and helps define how the universe preserves the consistency of cause and effect. The gravitational constant occupies a similar role in the laws of gravity. It sets the overall scale for the strength of gravitational interactions. If this constant were significantly larger, gravitational attraction would dominate everything, compressing matter quickly and possibly preventing stable planetary systems from forming. If it were far smaller, gravitational attraction would be too weak to gather gas into stars, leaving a universe with no radiance, no warmth, no fusion, and no structure capable of supporting life. The stability of familiar cosmic structures reflects the balance set by this constant. The reduced Planck constant plays an equally crucial role in quantum mechanics. It determines the scale at which quantum effects become significant, shaping the behavior of atoms, molecules, and all the processes that depend on quantization. Without this constant, the distinctions between discrete energy levels and atoms, which make chemistry possible, would not exist. Light would not be emitted in characteristic spectral lines. The richness of the material world emerges from the quantum rules defined by this constant. Another remarkable constant is the fine structure constant, a dimensionless number that describes the strength of electromagnetic interactions. It governs how electrons bind to nuclei, how atoms emit light, and how chemical bonds form. If this constant were slightly different, the patterns of atomic spectra would change, altering the properties of all matter. Chemistry as we know it depends sensitively on this number. Many physicists have noted that the fine structure constant seems almost just right for a universe that supports complex structures. These constants do not simply appear in separate contexts. They often work together in subtle ways. Particle physics, cosmology, and quantum theory all rely on combinations of constants that shape the evolution and structure of the universe. The proportions between different constants determine how forces compare in strength, how particles behave, and how the early universe evolved after the first fractions of a second following the Big Bang. Even the formation of galaxies and the spread of cosmic structures depend on the values of these constants. It is natural to wonder why these constants have the values they do. At present, physics does not provide a definitive answer. We can measure them with extraordinary precision, and we can describe how they influence physical processes, but we do not yet know why they take these specific values rather than others. Some theories propose deeper principles or symmetries that might fix their values. Others suggest that the constants could vary in different regions of a larger multiverse, with our particular set of values being one among many possibilities. These ideas remain speculative, but they illustrate how deeply the question of constants touches the foundations of reality. One might imagine that constants of nature could change over extremely long periods of cosmic time. Scientists have looked for such variations by studying ancient starlight, the spectra of distant galaxies, and the behavior of radioactive decay. So far, the evidence suggests that the constants remain unchanged, even across billions of years. This stability is essential for the reliability of physical laws. If constants drifted unpredictably, the universe would be far less orderly. Stars could behave erratically, chemistry might fluctuate, and the foundations of physics would be unstable. The constancy of these numbers is part of what makes the universe intelligible. In the framework of modern physics, constants often reflect the structure of the underlying fields. The mass of a particle, for example, arises not simply as an inherent attribute, but from interactions with fields permeating space. The Higgs field, discovered experimentally through the observation of its associated boson, plays a central role in giving particles their masses. This means that certain constants, which appear at first glance as arbitrary numbers, are actually tied to deeper mechanisms. Yet even here, puzzles remain. Why does the Higgs field have the strength it does? Why does it produce precisely the masses we observe? These questions point toward new physics we do not yet fully understand. Another important aspect of constants is that some of them are dimensionless. Dimensionless constants are pure numbers with no units attached. They do not depend on our choice of measurement system. These constants are often considered especially fundamental because they appear directly in the structure of physical laws, independent of human conventions. The fine structure constant is one such number. The ratios of particle masses are others. These numbers define the character of interactions, the stability of matter, and the scale at which different forces operate. The existence of these constants raises a deeper question. Could the universe have been different? Could the constants have different values, leading to a different set of laws and structures? Many theoretical physicists believe that the answer is yes. Small changes in some constants could lead to a universe with no stars, no stable nuclei, no chemical complexity, or no long-lived structures. Other changes might produce universes that are stable but vastly different in texture and behavior. Whether these universes are physically possible or merely logical possibilities remains an open question. But thinking about them highlights how delicately balanced our own universe is. Still, it would be misleading to suggest that the constants are tuned for a specific purpose. Physics describes what is, not what ought to be. The constants take the values they do, and the universe follows from those values. Whether one interprets this as evidence of deeper necessity, chance, or something else entirely is a philosophical matter. What science can say firmly is that the constants of nature define the rules by which the cosmos evolves. One of the most fascinating aspects of constants is how they unify seemingly unrelated phenomena. The same constant might appear in equations describing light, atoms, and the formation of stars. This repetition is not coincidence. It reflects the underlying unity of physical law. Constants serve as threads binding the tapestry of physics together. They allow theories from different domains to align, making it possible to connect the behavior of galaxies with the behavior of electrons. Without constants, the laws of physics would be a scattered collection of unrelated rules. With them, the universe becomes coherent. As research continues, physicists hope to understand whether these constants are truly fundamental or whether they emerge from deeper structures. Some theories of quantum gravity or unified fields propose that the constants might themselves be derived quantities. If so, the deepest laws of nature would involve even more fundamental elements from which the constants arise naturally. But until such theories are confirmed, the constants remain the closest we have to fixed pillars in an ever-changing universe. When you reflect on this, it becomes clear that the constants of nature give the universe much of its character. They determine the rhythm of cosmic evolution and the stability of matter. They shape the behavior of particles and the formation of stars. They are the quiet numbers behind every sunrise, every breath, every atom in your body. And as the day comes to a close, there is something calming in the idea that while so much in life shifts and changes, the deep constants of nature remain steady. They hold the universe in balance, gently guiding its evolution from one moment to the next. You are part of that balance, carried effortlessly by the unchanging numbers that shape everything, from the smallest particle to the largest galaxy. Let that quiet steadiness ease your thoughts as you drift toward rest, knowing that the universe remains stable, calm, and continuous around you. Chapter 7. The Emergence of Rules: Why Laws May Not Be Fundamental. When we speak about the laws of physics, we often imagine them as timeless commandments written into the fabric of the universe. They appear stable, general, and unchanging. They govern the motion of planets, the behavior of atoms, the flow of radiation, and the structure of space itself. Yet one of the most intriguing developments in modern physics is the idea that these laws, solid and universal as they seem, might not be fundamental. They may instead emerge from deeper processes, just as the properties of a liquid emerge from the collective behavior of molecules. In this view, the universe's apparent order is not imposed from above, but arises from the bottom up, from patterns and processes more basic than space, time, matter, or force. To understand this possibility, it is helpful to consider what emergence means in physics. Emergence is a phenomenon in which the collective behavior of many components gives rise to new properties, new rules, and even new kinds of objects. These emergent features are not obvious from looking at the individual components alone. No amount of staring at a single water molecule will tell you about the fluidity of water. No single grain of sand suggests the behavior of a shifting dune. A lone neuron does not explain thought. In each case, the whole is genuinely different from the parts, not because the parts violate any laws, but because their interactions create new patterns at larger scales. In physics, emergence appears everywhere. The classical behavior of gases, for example, arises from statistical patterns in the rapid motion of countless molecules. Temperature and pressure are emergent concepts, meaningful only when considering the large collection of particles. Likewise, the rigidity of a solid, the ability of superconductors to carry current without resistance, or the behavior of magnetic materials, all depend on collective effects. None of these behaviors can be predicted simply by examining a single atom or molecule. They exist only at higher levels of organization. When physicists began to examine quantum field theories more deeply in the 20th century, the idea of emergence took on a new significance. The notion that physical laws might change depending on the scale at which one observes a system led to the development of renormalization group theory. In this framework, the behavior of a system at different energy scales can be profoundly different. At high energies, one set of rules may apply. At lower energies, effective rules emerge that describe the behavior of the system in a simpler, averaged way. These effective rules may look like fundamental laws, but they are not truly fundamental. They describe the behavior of a system only within a particular range of conditions. An excellent example comes from the physics of fluids. At a microscopic level, a liquid consists of molecules colliding with one another, interacting through electromagnetic forces. But at the macroscopic level, we do not describe water by tracking each molecule. Instead, we use the equations of fluid dynamics, which treat the liquid as a continuous medium. These equations are incredibly accurate for predicting the behavior of water at large scales. Yet they are emergent. They arise from deeper rules that govern the molecules. Nothing in the molecular laws explicitly says that water should have waves, vortices, or turbulence. Those patterns appear only when countless molecules move together. This layered structure of physical description suggests that some of the laws we treat as fundamental may themselves be effective laws. They may emerge from even deeper levels of reality that we do not yet fully understand. For example, space-time itself, the stage on which all physical processes unfold, may not be fundamental. Several modern theories, including certain approaches to quantum gravity, propose that space-time emerges from more basic building blocks, such as networks of relations, quantum entanglement patterns, or discrete structures that do not resemble space or time at all. In such theories, the geometry of space-time appears only as an emergent phenomenon, valid at scales much larger than the fundamental constituents. If space-time is emergent, then the laws that govern it, such as those of general relativity, would also be emergent. They would reflect the collective behavior of deeper degrees of freedom, as much as fluid dynamics reflects the behavior of molecules. This idea is both profound and unsettling. It suggests that gravity, one of the most familiar and universal forces, might be a large-scale approximation of something more fundamental. Even the constancy of physical constants could, in principle, be emergent from processes that average out fluctuations at deeper levels. Quantum mechanics also hints at emergent behavior. The classical world we observe, a world of solid objects, local interactions, and definite properties, emerges from underlying quantum rules that are probabilistic and non-local. Decoherence theory shows how the quantum world, full of superpositions and entanglement, gives rise to classical patterns when systems interact with their environment. The classical laws of motion, once thought to be foundational, are now understood as approximations that hold when quantum effects become negligible. They are emergent laws, not fundamentally etched into the universe. Emergence is not a sign of incompleteness. Instead, it is a natural feature of systems with many interacting components. It helps explain why different scales of physical description can appear disconnected. A biologist does not need to understand quantum field theory to understand how cells divide. A chemist does not need general relativity to predict the structure of molecules. Each layer of reality has its own rules, its own patterns, and its own emergent laws. Yet these layers remain connected in subtle ways, forming a continuous hierarchy from the smallest scales to the largest. The possibility that the laws of physics themselves may emerge invites us to rethink the concept of law. Instead of treating laws as fundamental commands, we can see them as stable regularities that arise from deeper structures. This perspective does not diminish their power. Emergent laws can be just as precise, just as universal, and just as mathematically beautiful as fundamental ones. But their origin lies in collective behavior rather than intrinsic necessity. One of the fascinating implications of emergence is that it may explain fine-tuning in the universe. Certain properties of the cosmos appear delicately balanced to allow the existence of complex structures. If the laws are emergent, then some of this fine-tuning may be a natural consequence of deeper processes that average out variations. Just as temperature settles into equilibrium in a gas, some features of the universe may represent equilibrium states of more fundamental degrees of freedom. The apparent tuning could then be a reflection of stability rather than coincidence. Emergence also plays a key role in cosmology. The early universe underwent a series of phase transitions, during which symmetries broke and new structures formed. The laws that govern the universe today may be the result of these transitions. At extremely high energies, the forces may have been unified, but as the cosmos cooled, they separated into the distinct interactions we observe now. This means that the laws of physics may have evolved over cosmic time, changing as the universe passed through different stages. Our current laws might be only one chapter in a longer story. In this context, the question of whether laws are fundamental becomes more nuanced. Even if some laws emerge from deeper principles, those deeper principles might themselves be governed by symmetries or structures that appear law-like. Emergence does not eliminate the possibility of deeper rules. It simply shifts the foundation. The fundamental laws may operate at levels we cannot yet probe, and what we see at human scales may be the outer layer of a nested hierarchy. The quest to understand emergence spans many fields of physics. In condensed matter, researchers explore how collective quantum states give rise to phenomena like superconductivity and superfluidity. In high-energy physics, theorists investigate how particles and forces might arise from deeper symmetries or from the geometry of extra-dimensional spaces. In quantum gravity, the challenge is to show how space-time itself could emerge from structures that do not resemble it in any obvious way. Across all these areas, the idea of emergence unifies what might otherwise appear to be unrelated questions. The philosophical implications are equally striking. If the laws of physics are emergent, then the stability of the universe is not guaranteed by some external order, but by the internal coherence of its foundational processes. The cosmos becomes a kind of self-organizing system in which order arises naturally from underlying interactions. This perspective resonates with ideas in complexity science, information theory, and even biology, suggesting that emergence may be a universal principle, not limited to physics alone. As you reflect on these ideas, there is something comforting in the notion that order can arise from within. The universe does not require external guidance to form stars, galaxies, molecules, or life. Patterns emerge because the underlying structures allow them to. Laws appear because the universe itself settles into stable forms. And in your own life, patterns emerge too. Habits, emotions, insights, memories. They are not imposed, they arise from the interactions within you. Just as the cosmos finds order through its deepest structures, you find order through your own. Let that quiet parallel settle within you as the day recedes, reminding you that emergence is not only a physical principle, but a gentle rhythm that shapes both the world around you and the world within. Chapter 8. The Changing Universe. Do the laws evolve over time? One of the quiet assumptions built into modern physics is that the laws of nature are fixed. We treat them as unchanging, universal, and absolute, applying equally on Earth today, in a distant galaxy millions of years ago, or in the unimaginable heat of the early universe. This assumption has been extraordinarily successful. It allows physicists to interpret ancient starlight, decode the history of galaxies, and reconstruct the earliest moments after the Big Bang with remarkable precision. Yet the question remains, must the laws of physics always have been the same? Could they evolve? Could the universe itself transform in ways that subtly reshape the rules that govern it? To explore this question, it helps to recall that the universe does change. It is not static. From the earliest hot plasma to the emergence of stars, from the formation of galaxies to the quiet drifting of modern cosmic structures, the universe has undergone profound transformations. Matter has rearranged itself, temperatures have shifted, densities have fallen, and symmetries have broken. The cosmos today is unimaginably different from what it was in its first instance. It would be surprising if the universe could change so dramatically in its visible properties without any evolution in the deeper structures that shape those properties. One way in which physicists frame this possibility is by considering whether the constants of nature might vary over time. These constants include the strength of gravity, the speed of light in a vacuum, and various parameters associated with quantum interactions. Modern measurements suggest these quantities have remained strikingly stable over billions of years. When physicists examine the light from ancient quasars, the behavior of radioactive isotopes in geological samples, or the patterns in the cosmic microwave background radiation, they see no clear evidence that the constants have drifted. But this does not rule out the possibility entirely. It simply shows that if such evolution occurs, it must be subtle, confined to transitions in the deep early universe, or present only in ways we have not yet been able to detect. Another way the laws might have changed is through the breaking of symmetries in the early universe. At extremely high temperatures, far beyond anything achievable in laboratories today, the universe may have obeyed a set of unified laws. In this picture, the different fundamental forces we now recognize as separate, the electromagnetic, weak, strong, and gravitational interactions, may once have been merged into a single interaction. As the universe expanded and cooled, this unified symmetry could have fractured, splitting into the familiar forces. Such symmetry breaking would not be a minor detail. It would represent a genuine evolution of physical law, in which the kinds of interactions possible in the early universe simply no longer exist today. This idea is not purely theoretical. Experiments in particle physics reveal how symmetries can break and generate new behaviors. The weak nuclear force, for instance, has properties that emerge from the breaking of a deeper symmetry. In this sense, the universe already displays examples of physical rules that depend on its state. The laws that govern interactions today are not identical to the rules that governed them when the universe was far hotter and denser. This is a form of evolution in the laws, driven not by time directly, but by the changing conditions of the cosmos. Another profound possibility arises from the idea that space-time itself may not be fundamental. If space-time is emergent, arising from deeper quantum structures, then the laws that depend on space-time, such as the rules governing gravity, would also be emergent. In that case, the behavior of the universe at the largest scales might evolve as the underlying quantum structure evolves. This would not necessarily violate any observations, because such changes might occur only at the most extreme energies or only in the earliest epoch of the universe. Nevertheless, the concept introduces a subtle form of evolution in the rules of nature. The laws could be stable at familiar scales, yet different at scales we cannot yet access. Cosmology provides further hints that the laws might shift over vast stretches of cosmic time. The expansion of the universe, for example, is driven in part by dark energy, a mysterious component of the cosmos whose behavior is still not fully understood. If dark energy's properties change, if its density evolves or its behavior transitions, then the large-scale structure of the universe might follow different rules in the future than it has in the past. This would not necessarily alter the fundamental laws themselves, but it would change how those laws play out across cosmic scales, effectively altering the dynamic rulebook of the universe. Another area of active exploration concerns the concept of varying dimensionality. Some theories suggest that the number of effective spatial dimensions might depend on scale or energy. At extremely high energies, the universe might behave as though it has fewer dimensions, while at lower energies, more dimensions emerge. If this view is correct, even the dimensionality of space, the arena in which physical laws operate, might evolve. This would profoundly alter the nature of physical rules across different cosmic epochs. When contemplating whether laws might evolve, one must distinguish between changes in the laws themselves and changes in the emergent behavior described by those laws. As discussed earlier, many laws in physics are effective, meaning they describe the behavior of systems at particular scales, but may not apply universally. The laws of fluid dynamics, for instance, are emergent from microscopic molecular rules. As conditions shift, temperature, pressure, density, the emergent laws change. If the universe can be viewed as a vast emergent system, then some of the laws we take as fundamental might be scale-specific approximations that evolve as the conditions shift. This idea is echoed in the renormalization group approach of quantum field theory. In that framework, the behavior of a system changes as one moves from one scale to another, with certain interactions becoming more or less important. If one applies this concept to the universe itself, it becomes natural to think that the laws governing the cosmos might depend on scale and energy. The early universe, at extremely high energies, would follow a different set of effective laws than the universe does today. These differences would not violate the consistency of physics. They would reflect the fact that the laws we observe now may be the large-scale, low-energy limits of deeper principles. Even within established physics, the concept of law evolution appears in subtle ways. Consider the early universe's rapid expansion, known as inflation. During this phase, space-time expanded exponentially, smoothing irregularities and stretching quantum fluctuations into cosmic seeds. The rules governing this inflationary phase were different from the rules that govern the universe today. After inflation ended, the universe cooled, matter formed, and a new set of rules took over. The transition between these regimes is not fully understood, but it likely involved deep shifts in the behavior of fields and forces. Some speculative models go further, suggesting that the laws themselves might have evolved gradually, not just in abrupt transitions. These models explore whether certain constants might slowly drift, or whether deeper symmetries might unfold over cosmic time. While evidence for such gradual changes is limited, the very possibility opens new ways of thinking about physical law. Instead of seeing laws as eternal truths, one can imagine them as stable phases of a deeper dynamic reality. One must also acknowledge the philosophical implications of law evolution. If the laws of physics can change, even in principle, then what does it mean to say that something is fundamental? Are there deeper, unchanging principles that give rise to these evolving laws? Or are the laws themselves part of a broader, self-organizing system in which even the most basic quantities emerge from underlying processes? These questions blur the line between physics and metaphysics, inviting reflection on the nature of explanation itself. What remains clear is that the universe's history is not static. It has evolved from simplicity into complexity, from uniformity into structure, from high-energy symmetry into the differentiated interactions we observe today. Whether the laws themselves evolved, or whether they revealed different faces under different conditions, the cosmos has grown, changed, and transformed over billions of years. The universe today is not the universe that once was, and it will not be the universe that someday will come. And as you think about this long cosmic evolution, it may be comforting to recognize a parallel in your own experience. You too evolve. Your thoughts, habits, emotions, and perspectives shift with time. New patterns emerge, old ones fade. Just as the universe passes through phases of expansion and cooling, through transitions that reveal new structures, your own life moves through chapters shaped by change. There is no need to resist this transformation. It is part of the natural rhythm of existence. The cosmos evolves, and so do you. And within that shared movement, there is a quiet reassurance. The sense that change is not a disruption, but a gentle unfolding of deeper possibilities. Chapter 9. Beyond our universe, could different realities have different laws? When we speak of the laws of physics, we typically mean the specific set of rules that govern our universe, the behavior of gravity, the structure of quantum fields, the constants that shape the formation of stars and atoms. These familiar laws provide the foundation for everything we can see and measure. Yet, many lines of modern scientific thought point toward a startling possibility. The laws we know may not be the only laws that could exist. Other realities, if they exist, might be governed by entirely different rule sets. These could be variations on our own laws or something profoundly unlike anything we can imagine. The study of such possibilities is not idle speculation. It arises naturally from several deep questions in physics and cosmology. To understand why physicists take these ideas seriously, it helps to begin with a simple observation. The laws of our universe depend on particular values of physical constants, and these values are not logically necessary. They could, as far as we can tell, have been different. The gravitational strength, the masses of particles, the strength of electromagnetic interactions, the rate of cosmic expansion. None of these numbers follow inevitably from first principles. Instead, they appear as given features of our reality. If they had been even slightly different, galaxies might never have formed. stars might never have ignited, and atoms might not have been stable. This sensitivity to initial conditions suggests that there is nothing inherently privileged about our universe's particular laws. They are one set of possibilities among many conceivable alternatives. Modern cosmology extends this idea even further. The theory of cosmic inflation, which describes the rapid expansion that occurred shortly after the Big Bang, allows for the possibility that inflation might occur in different regions of space-time in different ways. In some models, inflation does not end everywhere at once. Instead, pockets of space stop inflating at different times, forming bubble universes, each of which expands into a universe with its own properties. The process can continue indefinitely, generating a vast or even infinite collection of distinct regions, each potentially governed by different physical constants or different patterns of symmetry breaking. If this picture is correct, our universe is just one branch in a much larger tree of cosmic growth. Of course, these other universes would be beyond direct observation. The distances separating them would grow far faster than light could traverse. Yet the mathematics of inflation makes their existence a natural consequence of the theory, even if we can never access them. In such a scenario, the laws of physics might not be fundamental truths, but outcomes of a larger cosmic landscape, where different regions settle into different vacuum states with different rule sets. Another line of reasoning arises from string theory, a framework that attempts to unify quantum mechanics with gravity. In these models, the universe has more dimensions than the four we normally experience. The extra dimensions are compactified or curled up in specific shapes, and the geometry of these compact dimensions determines the physical constants and laws that emerge in the larger universe. Because there are many possible shapes these extra dimensions could take, string theory naturally leads to a huge variety of possible universes, each with its own laws. This vast space of possibilities is sometimes called the string landscape. In this view, the laws of physics we observe are not unique, but are one selection among an enormous number of possible configurations. The idea that different realities could follow different laws also arises from quantum mechanics. In the many worlds interpretation, every quantum event splits the universe into multiple branches, each representing a different outcome. These branches share the same fundamental laws, but the distribution of matter and energy diverges over time. While this version of many universes does not involve different rule sets, it underscores the idea that reality might not be limited to one unique history. It suggests that what we perceive as the universe might be only one slice of a much larger and richer structure. The possibility of different laws also prompts questions about what it means for a law to be possible in the first place. Are all mathematically consistent laws physically meaningful? Could there be universes that follow rule sets utterly unlike anything we know, with interactions and structures that have no analog in our world? The truth is that we do not know. Physics is shaped by what can be discovered and tested in our universe. Beyond that, we operate in the realm of theoretical possibility. Yet the fact that our universe's laws are not logically predetermined leaves open the possibility that other laws could exist and perhaps do exist in realities beyond our observational horizon. One of the most intriguing questions in this context is whether universes with different laws could support structures analogous to atoms, stars, or life. It is easy to imagine slight variations that render a universe sterile. But could there be alternate sets of laws that give rise to entirely different forms of structure or complexity? The answer is not clear, but the question reminds us that our universe's habitability may not be an accident. If many universes with different laws exist, we naturally find ourselves in one of the rare universes capable of supporting observers. This line of reasoning, while philosophical, connects back to the scientific puzzle of fine-tuning. If the constants appear delicately balanced, it may be because we inhabit the subset of universes where balanced values permit complexity. At a deeper level, contemplating different realities forces us to reconsider the nature of physical law itself. If the laws can vary from one universe to another, then they are not absolute truths, but expressions of particular conditions. This perspective resonates with the idea of emergence discussed earlier. Just as macroscopic laws can emerge from microscopic dynamics, perhaps the fundamental laws we observe emerge from deeper structures that can take different forms. In this sense, universes with different laws might reflect different stable solutions of more fundamental principles. There is also the question of what it means for a universe to exist. Could universes with incompatible laws coexist in a broader structure of reality? Could there be universes with no space-time geometry, no familiar matter, or no quantum behavior? Theoretical physics entertains such possibilities, not because we have evidence for them, but because our best frameworks do not rule them out. If space-time and quantum fields are emergent, then there could be other ways in which reality organizes itself, producing laws that do not resemble our own. All of this might seem speculative, but it helps illuminate a crucial point. The laws of physics, as we know them, are intertwined with the specific structure of our universe. They are not detached axioms floating in a void. They are expressions of the universe's deep architecture. If that architecture were different, the laws would be different. And if other architectures exist, even only as theoretical possibilities, they broaden our conception of reality. In the search for deeper understanding, physicists push these ideas further, attempting to determine whether there are meta-laws, rules governing which sets of laws are possible and how they arise. If such meta-laws exist, they might define the boundaries of the cosmic landscape. They might explain why some universes are possible and others are not, or why some produce complexity while others fade into uniformity. But these questions remain open, lying at the frontier of theoretical science. Reflecting on these possibilities can evoke a sense of both wonder and humility. The universe we know is vast, but it may be only one part of a far greater structure. The laws we rely on, laws that allow stars to shine and atoms to hold together, may be only one variation among many. Yet despite this vastness, you inhabit exactly the universe whose laws allow your existence. The constants, the fields, and the symmetries all align in a way that makes your life possible. And as you settle into the quiet of the evening, it is calming to remember that even if countless other realities might exist beyond our reach, you are part of a universe that supports breath, thought, warmth, and meaning. Let that sense of belonging to this particular reality ease your thoughts as the night draws in, reminding you that in a cosmos of infinite possibilities, your existence is one of them, a quiet and remarkable outcome of the laws of this universe. Chapter 10. Why the universe has rules at all. The philosophical reflection. When we ask why the universe has rules at all, we step into one of the deepest questions in both physics and philosophy. It is a question that scientific theories alone cannot fully answer, because it sits at the border of what physics can describe and what human reason can contemplate. Yet physics provides essential clues. By examining the structure of physical laws, the stability of constants, the universality of symmetries, and the emergence of order across cosmic scales, we gain insight into the nature of rulefulness itself. What begins as a scientific inquiry gradually becomes a reflection on the meaning of order in a universe that could have been chaotic. To appreciate why the existence of rules is remarkable, imagine a universe with no regularities. In such a cosmos, interactions would not follow predictable patterns. Stars could not form because gravity would not behave consistently. Atoms would not exist because the forces holding particles together would fluctuate wildly. Even the notion of time would lose coherence, because without stable laws, there would be no reliable way to distinguish one moment from the next. A chaotic universe might flicker into existence only to dissolve again in an instant, unable to support enduring structures. The fact that our universe is not like this, that it has predictable, stable rules, is a profound feature that demands explanation. One way to think about why rules exist is to consider the role of symmetry. As earlier chapters explored, symmetries constrain the form of laws. They tell us that physical laws must look the same from one place to another, from one time to another, and from one orientation to another. These symmetries give rise to conservation laws, which in turn anchor the stability of the universe. In this sense, symmetries do not merely constrain laws, they make laws possible. If the universe lacked these symmetries, consistent rules about energy, momentum, or angular momentum would not exist. Symmetry thus provides a partial answer to the question of why rules exist. They emerge naturally from the requirement that the universe not depend on arbitrary choices of perspective. But this raises another question. Why does the universe exhibit these symmetries in the first place? Is symmetry a necessary feature of any coherent reality, or is it contingent, a fortunate accident of our cosmos? Some philosophers argue that without symmetry, no stable structures could exist, so symmetry may be a prerequisite for any universe capable of sustaining complexity. Others propose that symmetry emerges statistically in large systems, and some views suggest that the symmetries we observe are only approximations, arising from deeper, less symmetric structures. If symmetry itself is emergent, then the rules built upon it may be emergent too. Another perspective focuses on the mathematical character of physical laws. Mathematics provides a clean, precise language for expressing the relationships that govern the universe. The fact that nature can be described by mathematics suggests a deep connection between physical reality and logical structure. If one accepts that mathematical structures exist independently of the physical world, then one might argue that the universe has rules because it instantiates a particular mathematical structure. This idea, though philosophical, aligns with the remarkable success of mathematical reasoning in physics. The universe behaves in ways that mirror the internal consistency of mathematics, as though physical processes are expressions of logical relationships. Yet it would be simplistic to claim that mathematics alone forces the universe to have rules. Mathematics describes possible structures, but physics tells us which structures correspond to reality. The laws of physics are not arbitrary selections from a mathematical catalog. They are rooted in observation and experiment. Even so, the uncanny match between the mathematical world and the physical world invites reflection. Why should nature be intelligible in this way? Why should its behavior fall into patterns that can be captured by human-made symbols, equations, and abstractions? Some physicists propose that the universe's rulefulness arises from the need for consistency. For a universe to exist in a coherent way, the interactions within it must not contradict one another. If fundamental behavior were inconsistent, the universe might not form stable categories at all. Consistency may therefore be a foundational requirement, and the laws we observe could be the most stable, consistent structures available. This idea resembles the way certain languages develop grammatical rules, not because someone imposes them, but because consistency enables communication. Similarly, the universe may follow rules because rules are the only way for reality to persist coherently. Another line of thought stems from the idea of emergence. The rules we call fundamental may arise from deeper, pre-physical processes. Just as temperature, pressure, and fluid dynamics emerge from molecular behavior, the apparent laws of physics might arise from interactions at levels we cannot see. If space-time itself is emergent, then the laws built upon it, gravity, causality, even the dimensionality of space, may emerge too. In this view, the universe has rules because emergence favors stability. Systems made of countless interacting elements naturally settle into stable patterns, and these patterns appear as laws. Rather than being imposed from outside, the laws are outcomes of the universe's internal self-organization. A related idea considers information as fundamental. According to certain interpretations of modern physics, the universe may be understood as an information processing system. Quantum states encode information, fields carry information. Space-time geometry might reflect information flow. In this perspective, laws exist because information must transform according to consistent rules. Without consistency, information could not persist or propagate, and the universe would not form enduring structures. The laws become the grammar of cosmic information. Still, these reflections address only part of the question. One might still ask why any regularity exists at all. Why does the universe not express pure randomness? One possible answer is anthropic. We observe laws because only a universe with laws can support observers. Without stable structures, no conscious beings could arise to ask why the universe has rules. This answer, while logically sound, leaves open the deeper question of whether the existence of observers plays any genuine role in the universe's rulefulness, or whether it is simply a consequence of the universe's stability. Physicists also consider the possibility that the universe's rules are one possible outcome among many. If there exist many universes with different laws, as discussed in the previous chapter, then the question shifts from why these laws to why this universe. In a vast landscape of possibilities, the existence of laws may be commonplace. Our universe, then, might not be special. It might simply be a region of a much larger reality where stable laws happen to hold. This idea does not diminish the significance of the laws. It just places them within a broader context. There is also a perspective grounded in humility. Perhaps the question of why the universe has rules is ill-posed, in the sense that what we call rules may be simply the most accurate patterns we have found so far. As our understanding deepens, what looks like a rule might turn out to be emergent, approximate, or context-dependent. Even so, the presence of patterns at any level remains striking. Whether fundamental or emergent, the universe's rulefulness is what makes science possible. Without it, we would inhabit a world that could not be known. As we reach the end of this journey through the nature of physical law, one thing becomes clear. The existence of rules is not merely a physical fact. It is also a philosophical treasure. It tells us that the universe is not a meaningless swirl of events, but a place where patterns endure, where behavior can be understood and predicted, where structure forms from simplicity, and where complexity grows from underlying order. The laws do not constrain us. They reveal the profound coherence of the cosmos. And as you settle into rest, there is comfort in knowing that beneath the surface of every moment, there is structure. Beneath the uncertainty of daily life, there is a quiet order that does not depend on fear or effort. The same laws that shape galaxies shape the rhythms of your own body. The same stability that governs the universe offers a sense of steadiness within you. Let that awareness soften your breathing and ease the day away, reminding you that you too are part of a cosmos held gently together by its quiet, enduring rules. And that's our quiet journey for tonight, my friend. I hope your mind feels a little lighter and your breath a little slower. If you're still awake and want to drift deeper, I left another calm video waiting for you on the screen. It's right there whenever you're ready. And if you're already sinking into sleep, then sweet dreams among the stars. Good night.